Welcome everybody. So today we are just having done the introduction and just motivated some of the basic ideas uh, of symmetries and some sort of idea of the structure of differential equations yesterday through the nozzle example. Today we'll just look at another extremely important example from electrostatics. So we'll just try to understand what your structure of um, like your solutions can be. So for example, one thing we already know is that we have this Taylor series, right? We have for expanding anything, get going into detail. You need the Taylor series. You're just trying to just use the Taylor series to expand a function, and then you take whatever level of approximation that you want. That works, right, most of the time. If normal straightforward solutions are not working, then your Taylor series steps in, right? So similar to that, we'll just look at something else today. Right, for that, let's just consider um, a charge distribution. Okay, the charge distribution is localized in some some radius r prime. Sorry. So let's say, so what happens is, this is another method that physicists use, right? The methods of scales and how for example, if something is of negligible order compared to whatever you're working at, like whatever scale you're working at, you just say that the order is like infinitesimal, and you make some approximation to neglect that, but you don't completely neglect it. So you use some sort of weak methods, such as series expansion, to kind of get that right. So if you're not able to analytically compute that particular thing. So right, for this example, let's take this thing. Let's take just a charge distribution. The So in this, let label this. Let's approximate this to a sphere of radius r prime. So now we know that so this is a vector, r prime is a vector. So suppose we have origin somewhere here, and then there is a charge distribution around the origin with the vector r prime, right? So and the volume of this thing will be d3x, or v prime, that is corresponding to the r prime. We have a v prime, right? So this is the volume. Now we want to measure the potential of this with respect to some other point P. Okay, so okay, just let me make things a little bit clearer. Okay, so let's say the origin is here, this is the O, and this is of r prime. Okay, and so you have r prime here, and then you have this is your r. So the radius from the charge to the point where you're trying to measure your potential, that is r, right? Now how do you write the potential at r? Any takes? Okay, it's simple, right? Like you have 1 by 4 pi epsilon naught, which is always there, the constant, and then you have an integral over the charge density. So given some charge density, obviously this has to have some charge density rho of r. Right? So you have a charge density which is a function of r prime by the separation of by this separation, right? By this vector. So by r minus r prime. So basically you're measuring the potential at the origin, which is 0, and then you're just like, I mean it's not 0, but like you just have some sort of a potential at the origin, and then you're like taking that displacement with respect to the charge density. So yeah, you're just figuring out where the charge is, and then you're like taking it to the next this time, right? So this O need not be exactly outside the charge distribution. I've just indicated in the diagram to make sure there are like no confusion. So yeah, and that everything is small and so and such. So right now we have this, and then you have to integrate this over the volume in which all the charge is confined to. So you have integrate over dv prime, and the boundary condition being the regions where all the charge exists, right? So given this, this is your expression. Right now, when you do calculate like your integral, your the thing is your density is a little like if it's so you need a clearer idea, right? In normal electrostatics, so for example, if you have uniform bodies and if you have like say spherical bodies or something that is easily integrable, like for example like where you can easily figure out what the v prime is. So if you can just easily figure that out, then your integral becomes like more or less like solvable, and then you can just write it down. Even then, you still need to expand this, and then you need to kind of like work this down. So this the denominator here, it is the major issue here, because you really have you have two variables. So you have r prime and you have r as well. So where r is a more general like variable of the global variable, here r prime is your integral. It gives you your internal distribution, charge distribution. So now given like now how do we do this? How do we go about with this? So for this we need to expand r the denominator. That's like probably that's the like only way that you can go about with it. And actually by expanding the denominator, we find out that it has something hidden to it, hidden in it, right? We find that like as we expand the denominator, it condenses to give you a picture which is the twist waiting in a bit, which gives you like more insight into this like whole like structure of nature of like the charge distribution, etc. So now like just to expand this, right? So you have you want to write down r minus r prime as root of r square minus 2r dot r prime plus r prime square, right? So this is just basically square root of r minus r prime, the whole square, right? So which is the modulus, right? Fair enough. Now what you want to do is you want to take out r from this, the magnitude of r from this. So we have r root of 1 minus 2 r cap, that is the direction vector, So you don't have the magnitude, but you just have the, let me make this a little more legible. Okay, r cap dot r prime y r plus r prime by r the whole square. So now here notice that you only have the magnitudes of r here, right? You don't there is only the one dot product here, which like takes your direction, but otherwise you're dealing with only the magnitude of r here. So essentially you have reduced the kind of like the dependency on the vector or the vector direction of r as well. So we have just taken it out of the square root, at least for now. Let's see what happens then. Okay, so yeah, as you know, like just okay, wait, why is this happening? Okay, so right. So as you know, r cap is nothing but vector by the magnitude of r. So now, right now, then you have the expansion of 1 by r minus, sorry, r minus r prime is 1, so 1 by r divided by root of modulus 1 minus 2 r cap dot r by r plus r dash by r whole square. Right? So the same thing. So we have written that down. Right? And now what you want to do, right? So in order to write this down explicitly, right? In order to write this term down, let me just quickly introduce what binomial theorem says. Okay, your binomial expansion says that, so this is, okay, I just need to make more space myself, right? So yeah, so your binomial expansion says that 1 plus x to the power of s is, it can be truncated into a series where you have the series as summation of m is equal to 0 to infinity, then you have s factorial by n factorial into s minus n factorial x to the power of n. So that is so this is this theorem, like basically originates from the very fact. As a refresher, this theorem basically originates from the fact. So for example, if you have x square plus y square, then you have plus y the whole square, you have x square plus y square plus 2xy, right? So that 2, the coefficient of 2 is calculated because you're like you need to multiply it 2 times. So when you take the brackets here, you just need to multiply things 2 times. So xy, that permutation combination happens 2 times, and that is exactly what this factorial is telling you. But except for taking one as like one variable and x as the other variable. Of course, like you do have binomial theorems in like both 2 variables and like you have something, but like on all of those cases. But this is the essential thing, right? So what you need to create, so what do you need to keep in mind here? You just need to keep this particular formula in mind, and note and understand how this factorial rises out of like the permutation and combination of the number of times you're multiplying this 1 plus x, right? So once you do this, you find that you can expand the series in the form of 1 plus s by 1 factorial x plus s into s minus 1 by 2 factorial x square plus s into s minus 1 into s minus 2 by 3 factorial s x cube plus da da da. So you have the whole like series continuation. Now what happens is, generally if your 1 plus x to the power of n is something that is convergent, right? If it is something that is convergent, or if it is something that you want to deal with as you know it's something that you want to deal with after, like you want to stop dealing with it after a finite number of like terms, right? So for example, like so that what is the condition then? What condition do we have then for like 1 plus x to the power of s to be convergent? Yeah, x can be very small, or s can be like, s can be like a root, or like a nth root. So in that way, then based on like the condition, so you have like several conditions for that. But essentially, when you when you have a convergent series like this, what we do is we find that beyond a particular scale, beyond a particular order. So for example, typically it is just the second or third order that you go to. You don't really focus on much more, because like yeah, so at least while calculating, of course in some cases, as when you're studying and when you're actually working out you problems, you will be expected to calculate up to the fifth order, sixth order, but like very rarely, and that is just to get a hang of like just computing the order, right? So but typically when you have a series and the series is convergent, you calculate the terms up to the second order or third order. Like once you get the hang of what is going on, you just like stop really computing it. So what you do here is what we want to do with this. So the whole reason why we were talking about this is we know that we can write this whole this particular thing as in terms of 1 plus x to the power of s. So how do we write that down? Any volunteers? So we want to write this particular term down in terms of 1 plus x to the power of s. Okay. So what you do here is you have 1 by 1 minus r prime is equal to 1 by r and to 1 by 1 plus epsilon. Well, then you have your epsilon is the small term, which is minus 2 r cap minus r cap r dot r prime by r plus r prime by r the whole square. So notice that even here, right, epsilon is usually infinite or like a small value. It is smaller than 1. So now the condition that we have taken is r prime is much smaller than r. So I forgot to mention it here specifically. So but you're working with the premise that r is much larger than r prime. So given this premise, so you can write this whole thing in terms of this, right? Uh, so now when you expand it, you actually end up getting 1 by r minus r prime is equal to 1 by r into 1 minus half epsilon plus 3 by 8 epsilon square minus 5 by 16 epsilon cube plus another. So you get a polynomial like of in terms of epsilon, like that. Okay. So now once you get this particular polynomial, then what you do is you can actually you realize that you write this 1 by root of 1 minus 2 r cap dot r prime by r plus r prime by r whole square is equal to 1 minus r cap dot r prime by r plus 1 by 2 r square, then you have r prime square minus 3 r cap dot r prime whole square plus you have order of r prime by r whole cube. So you have this, right? So once you try to expand epsilon in the above way, you just have this whole series, right? So now once you do that, what you find out is you can write down the potential now in terms of very simple thing, right? So how do you write your potential? Like given this, how do you write your potential? Okay, so this is the same as this, right? Just reminding. So this is the same as this. So how do you write your potential now? And take us. Okay. Let me just make the screen. Let me just cover the whole page. Just think for probably a couple of minutes, and then we'll move. Not really. Let's forget about the density. Let's pull out the density for now. Let's take okay, fine. Let's pull out the density, and we'll tell you another thing is we are actually talking about the density in terms of your expansion shelf now. So if you notice, okay, this is the tricky thing that I'm trying to this is the interesting thing that you have, right? Okay, fine. You have the density there as of yet, but apart from that, what do we do? You just have the density there, but what do we do apart from that? No need. I really don't have to. I just want to write down a simpler expression for the potential. That's it. Don't worry about the density, don't worry about the V prime, just focus on the R minus R prime. Okay, wait. Just you can take a look at it. So it's simple, right? So what we've done is we have expanded this, right? We have tried to expand this. So we have expanded 1 by r minus r prime in this way. So we just need to plug in this whole term in here. Like, so we have essentially, we have 1 by 4 pi epsilon naught integral with respect to v prime, like around v prime. Then you have rho of r prime, rho of r prime. Then you have 1 minus r cap dot r prime by r plus 1 by 2 r square, and then 3 of r cap dot r prime whole square minus r prime square plus order of whatever, right? R prime by r to the power of 3. So we have this, right? So based on this, now what we can do is we can write the whole VR. So this is the interesting thing, right? We can write VR, V of R is equal to V of the first term. So let's just say it as V1 plus V2 plus V3 plus so on. How does this work? It's simply because if you have integral of f of x plus g of x dx is equal to integral of f of x dx plus integral of g of x dx, right? So basically we can just expand this in terms of that. Now this is where the fun starts, because now if you just take off the density per se, and if you just assume there is a particular charge, okay, so you have charge at say 1 point or 2 points or 3 points, so on and so forth. So if you actually notice this, so you have like you have your as you go along, you have your charge at 1 point, which is just the integral of, so you have a monopole here, or like you have one charge, and then you have the expression for a dipole here, and then you have an expression for quadrupole, you have so on and so forth. So as you keep increasing the number of this thing, you keep increasing the number of charges. So then you have an analytic, like you have a function. So right, this is the way we stop talking about the charge density, and we just assume there are point charges. So we have reduced the problem of like imagining a convoluted charge density which has no real, like which doesn't like really make sense, like in the sense like if it is not analytical, you practically cannot integrate the function, or like so what you do now is you take that problem of the density, and you by expanding the r minus r prime, you have broken that problem down into the problem of charge distribution, localized point like charge distribution. So you have n charges, and what you can write down as you expect is you have oh sorry, V of mm, a monopole is equal to 1 by 4 pi epsilon naught into V prime, and then have rho of R prime dV. So now this actually it's very simple, right? Like as I said, rho is basically one, or like whatever unit of charge you want to put. So it's like 1 unit of charge, or like magnitude of charge. If not a unit, you have like a particular magnitude or magnitude, and then you have a dV. So you just have the volume. So for example, spheres or something like that, it's very simple to put it down in terms of volume. So thus you have a monopole. Then what you have V of a dipole is of R. Anyone wants to help me write this down? Hmm? Yeah, yeah. Mm-hmm. So, so yeah, you have integral of rho of R prime, then you have just R minus R prime. As in terms of the vector, like expansion, you can just write it down in terms of like the vector expansion. So you can just write it down as R cap minus R prime. Okay, so you just have the difference, like two charges and the charge density across the 2 points. So you have, basically this is the dipole moment. So that we have, so instead of like, so if you actually like look at the definition of a dipole moment, which is like what your P vector is. So this is what a P vector becomes, like whatever magnitude. The density decides the magnitude essentially, but that is a dipole moment. And then you have V quadrupole, which comes in the third order, like the second order expansion, that has 1 by 8 pi epsilon naught R cube. Okay, by the way, here I made a mistake. I have to write R square here, right? So yeah, so you have to write this. You have to bring this out, right? So yeah, so you have R square here, and then you have R cube, and yeah, so integral of rho of R prime, and we have 3 times R cap dot R prime whole square minus R prime whole square dV prime. So this is essentially what you have, right? So on you have like, quadrupole, like you have 8 poles, you have like so on and so forth, right? We can just keep going that. And then there is one more interesting thing about this particular series. It can only express things in terms of, for example, you don't have a tripole, right? You don't have a tripole. Why is that? Is something that you might want to think on. Why don't you have any odd number of poles? is something that you might want to think on. But mathematically, maybe like I'm just throwing around a couple of clues or like a couple of thoughts out here. But if you look at it, it's just expansion in terms of like you have like your two arcs here, and you have this the expansion written in terms of a square root of r square, something like that. So r minus r is equal to square root of r square minus square root of r square. So then, like, why explicitly do you have this kind of an expansion is something that you might want to think about. Give this a thought. So this understanding and coming to this whole like understanding, figuring out where the multipole expansion comes from. So this whole thing is so what we have done is we have basically done multiple expansion. Let me just write it down in the title. So also the calculations are correct, but haven't gone through each and every step of the calculation, so you will need to figure out where exactly the calculations are coming from, numbers, and especially pay attention to the vectors and all that. So basically now what you have is you have this one more thing that you probably need to keep in mind is that this integral is scalar. This is a scalar, and this integral is a vector, because you have like two vectors, like the subtraction of two vectors here, which is another vector, like within the integral itself, right? And density is like don't worry about the density. The density, like, just imagine it getting distributed along the vectors, or like whatever is the key term inside the integral in terms of r. Okay, so you have one vector here, so which is a dipole moment, like represented by a vector. Then you have like r, so you have r square term, so which means you have a bivector or a quadrupole tensor. So you have a vector scalar, then you have a vector, and you have a quadrupole tensor. So now there is one more method that I want to talk to you about. Just again, before going on into that method, what we have done, briefly summarizing, we have broken down the problem. Okay. Okay. Yeah. Sure. So what I was saying was, you just have if you look at it, if you look at the monopole expansion, you have multipole expansion. You have the first expansion, which is the monopole expansion, is a scalar, because it doesn't have any vector terms inside the integral, right? And the density is just dependent on the volume distribution, right? And then the second term, which is the dipole expansion, is a vector, because you have a vector, like two vectors, okay, like subtracted from each other, which is another vector. So then the third expansion, which is the quadrupole expansion, is two vectors, which is a bivector. So you have like dot product of two vectors, okay, which is a bivector. So you are actually dealing with a bivector, and you have like a bivector here. Even like the r square becomes so it becomes a tensorial expansion. So especially when you have like more number of things, more number of like particles, you can like expand a subset of this of the total number of charges using like, say for example, dipole expansions or quadrupole expansions. So you have like many quadrupoles and dipoles, etc. So in that subset especially, this becomes useful, like it becomes useful to talk about things in terms of a tensor. So you have a tensor, so you have a scalar vector tensor, and then like anything from here onward, like any number of vectors you have, like any arrangement of vectors, you have a tensor. So it's just all tensor expansion. So anything larger than a quadrupole expansion is a tensor like expansion. So it's something, it's a tensorial object. So yeah, that's basically it. Now so the key idea is, so in sometimes your problems in like impossible problems in like physics, for example, you can't figure out what rho of r prime is here, and then you completely you did this by uh, assuming that there are point-like charges. You actually do this by assuming that there are n point-like charges scattered in this density, and the number n tends to infinity. So you need to express r minus r prime, so in terms of like your n this thing, because r prime is like very identical for all the charges, okay, compared to r, but you just want to express r prime in terms of an infinite, like you want to express this in terms of an infinite number of like charges located within that particular volume. So then you have like n pole expansion, like a multipole expansion or n pole expansion. So where you talk about each charge as a pole, and like you have n poles, and then you just expand them, and you get this like whole, like you get the potential, you get the various potentials. Yeah. So one more like thing that so this is something that is again more or less an exercise slash problem solving kind of thing, slash homework, but let's talk about something completely disconnected for a moment. Okay, so you have something called as legendary polynomials. Okay, so the definition of so legendary polynomials are basically a category of orthogonal polynomials that are generated in very specific ways. So we will look at how these are generated, but before that we need to look at what orthogonal polynomials are. Okay, orthogonal polynomials have this definition. So minus 1 integral of minus 1 to 1. Okay, actually this is a definition particular to a legendary polynomial per se, but because the bounds of minus 1 to, based on the bounds minus 1 to 1, or like 0 to infinity, or minus infinity to plus infinity, so you have different categories, like you have 3 different like kinds of orthogonal polynomials. But legendary polynomials are those that are confined between minus 1 and 1. So the definition for orthogonal polynomials is if you have a polynomial of m degree in terms of x, and multiplied with a polynomial of n degree with respect to x, so the integral is 0 if n is not equal to n. And then it has to be some sort of a constant or a constant if m is equal to n. If m equals n. Okay, that is the idea here. So what is the meaning of orthogonal polynomial? Like how do you relate to this? Like what is the idea behind it? So it's not just about the integral that just cancel out, but it's also when you look at the specific shape of the curves, you see that they intersect at like orthogonal angles. So in the sense, like when you can't basically, if you have a vector, so tangent vector along a tangent along any two this thing, and you make that a vector, right? You take a tangent and then you can rewrite that as a vector. So you have the tangent for both the polynomials, and the dot product of the two should be 0. So basically the tangents are always orthogonal. So this is the essential definition of orthogonal polynomials. Now the particular way Legendre polynomials are defined or introduced is they have a very particular generator, right? The generator is basically, I mean, like, just go into this for just for the sake of it, right? Let's just try to understand like how some weird assumptions can lead to actually very interesting things, right? So the first weird assumption that you have is that you suppose that these orthogonal polynomials are generated from this relation. Okay, so 1 by 1 minus 2xt plus t square is equal to summation of Pn of x to the power of t to the power of n. Okay, from n is equal to 0 to infinity. So these polynomial generators are orthogonal polynomials. So why exactly, how exactly is something that is like I mean, you can fairly guess that it might have to do with like hey, you have like t minus you have some sort of like expansion in this, which makes you I don't know. So you have like some your t to the power of n generates some sort of like expansion where you have the tangent, like t probably fixes the tangent, right? So you don't like going into this is something that is probably for mathematicians. Like I haven't really gone into depth, but like you can ask the question. But essentially, this is just defined as a way to derive your legendary polynomials, right? So now what happens is, so if you expand up to the order t1, if you expand this thing up to order t1, you have p naught of x is equal to 1, then p1 of x is equal to x, right? And then for higher orders, you differentiate this with respect to t. So then you have x, so you differentiate both sides with respect to t, right? So then you have x minus t by root of 1 minus 2xt plus t square is equal to 1 minus 2xt plus t square times summation n Pn of x t to the power of n minus 1. So using these two relations, 1 and 2, you arrive at this particular equation, right? You arrive at n plus 1 p n plus 1 of x is equal to 2n plus 1 x p n of x minus p n minus 1 of x. So you have a series of, you can find out the n plus 1 term in terms of the p n term and the n minus 1 term. So you can find out, so you have a generator for the polynomial, right? So this is basically how you generate the polynomial, right? Now once given that, uh, now what you can do is you can indeed express your multipole expansion in terms of this, right? So you can express this as the multiple expansion. If you can think about it, you can express it as 1 by 1 plus eta square minus 2 eta x is equal to summation of eta to eta k p k of x. So then you essentially have your when you expand this, you find out that you get the same expansion as you had for a multipole expansion. So this particular series, so how this happens is also I won't be going into detail here, but I just want to figure out that I just like probably want to point out that one is you need to this is the homework, right? Like why is the legendary polynomials connected to the multiple expansion? How exactly are these two ideas connected? And how can you write what kind of what kind of function or like what kind of series can you represent in this particular manner with like the various Pn. Okay, so when you so when you write this down, you find out that you have the multiple expansion and so essentially your potential is proportional to is equivalent to 1 by r summation of a by r to the power of k p k cos theta. So just to figure out, like just to help you with this, let me give you the diagram. So you have so the charge density here, and then this is this particular so this is the origin. So you have A here, and then you have R, and then you have from the origin you have you have R. So given this, and then this is theta. So given this, given this geometric picture, or like into given this idea, this is the assignment is to find out how you can write down this particular expansion in terms of your legendary polynomials, like so that shall do the thing. So how do you write this down? Why is that to like derive this? So I've given you various discrete steps. I'll just send this to you as well, but it's essentially just various discontinuous steps, and I've shown you how a legendary polynomial can be derived, and I just like how do you connect these two things together. So that shall be the that's it for today.